Hello, Kingsport. Debbie, can you see and hear us okay?
Yes, we can.
Thank you.
You're welcome.
So the first thing is you have homework 4 for me. Make sure you get your name on those.
I'm sending it to you.
Better. Same.
I sent you a graph.
I didn't look at it all. You sent me the graph?
Yeah.
Well, I hope the graphs. So where we left off last Thursday, before I go back to the GMAT test, I want to put this up again, a randomized comparative experiment. And the reason I'm putting that up again is because, you know, look, there's two things we want to do here. We want to use randomization. What that means is, the simplest I can make it is, we randomly assign subjects to the treatments. The reason we do that is because then we don't have this problem with lurking variables. Right? In other words, so hopefully, you know, when we randomly assign these subjects to the treatments, these treatment groups, then the groups should all look the same. There should be nothing different from one group to the next. And then the other thing we always want to make sure we do is this comparative part of an experiment. And as simple as I can make that is we always want to make sure we compare treatments. If there's only one that we're interested in, then we'll come up with this control group and introduce the status quo, right? So that we have something to compare to. We will just never have a single treatment and go from there because that's no good. These are two big things we want to make sure we do. Randomization, comparative. Hence, the term randomized comparative experiment. Now look, later on tonight, I'm going to start giving you experimental designs. In other words, different ways to do a randomized comparative experiment. Every well-designed experiment that me and you do and talk about is always randomized and is always comparative. That's not an experimental design. That's the kind of experiment that we do randomized comparative. Now, back to my GMAT test and the online versus the classroom version, right? So what I want to do is I want to give you the outline. I don't want to write it all out in words. I want an outline of that experiment. And so you'll notice I have a single factor. It's how the class is offered to you. You have two levels. It's either the classroom version or the online version. So the one factor with two levels will give me two treatments, right? So the way it goes is this. Here sits my subjects. You know, the students that need this class. And just for the sake of things, let's say I got a nice number here and there's, I don't know, let's say we have 60. So I'm going to keep track of how many subjects I have. At this point here, I want to do some kind of random assignment. And what I think about doing, the simplest way for me to do the random assignment is to label these subjects, give them all labels 0, 1 through 60, and choose an SRS of 30 of them to go in the first group, and the 30 that's left over to go in the second group. And that's the same simple random sample from the previous chapter. So, I think about it like this. That random assignment is going to produce these two groups, and I'll have 30 in each, right? So I chose an SRS of size 30 went into group 1, the 30 that was left over went in group 2, and then this first group is going to get one of the two treatments. It doesn't make any difference. I'm going to call it treatment 1, and I'm going to say this is your classroom version. You remember how the class has been offered for years and years and years? And then this group here is going to get treatment 2. And that would be the online version. That's the one we were interested in. That's the new one. So we've randomly assigned the subjects to the treatments here, right, in my outline. Well, where's the comparative part come in? After you have imposed a treatment, after the students have taken the appropriate version of the course, we're going to, at the end here, you're going to compare. And what was this? This was the GMAT test, right? We're going to compare the GMAT scores. So I want to circle a couple things. There's the random assignment. There's the comparative part. All right? Now, I got a couple thoughts here. What's the only difference between these two groups? What's the only difference between the students taking the classroom version and the students taking the online version? The only difference here is the actual treatment they receive. In other words, how they took the class, right? That's it. That's the only difference. How do I know that? Because we randomly assigned the students to the particular classes. In other words, there was a problem last Thursday when we were looking at this where we just had the single treatment. Well, those people that were taking the online version, they were older, going back to school, that kind of stuff. Is that a problem here now? No, you'll have older students in both groups. You'll have younger students in both groups. You'll have people that are paying for it within both groups. The lurking variables are no longer a problem. I still haven't got to the punchline yet here, but this is like an outline, and this is an outline of a randomized comparative experiment where you have 2 treatments. Let me ask you this. Suppose I had another third treatment. You know, I got the classroom version, I got like a strictly online version, and I have a streaming version. What's my little picture look like? Instead of having 2 groups, there would be 3. Instead of having 2 treatments, there would be 3. And what would I do at the end? I would compare the GMAT results for the classroom version, the online version, and the streaming version. Now, you see that design? That is a randomized comparative experiment. That's why I circled in red. Randomly assign the subjects, compare the treatments. Experimental designs. There is more than one. It's just like sampling designs. How do you choose a sample? We had 4 good ones, right? Well, experimental designs, our first one is something called completely randomized. The definition is on page 237. I'm going to read it to you instead of writing it up. And what it says is, in a completely randomized experimental design, the setup of your randomized comparative experiment, all the subjects are allocated at random among all the treatments. See that one? That's a completely randomized design. Is it a randomized comparative experiment? Absolutely. The experimental design is completely randomized. What does that mean? It means you got all these subjects in a pile and you randomly assign them to the treatments, however many treatments that you have. Right? That's our first one. Now, that's an experimental design. There's still randomized comparative experiments. That's how you set it up. You just randomly assign the subjects to the treatment without any other thought about anything. And then you start giving treatments and then you compare your response variable in the end. That's what you do here. All right? Now, I'm thinking about what I want to... Let's get to the point of the matter. All right? I've got 2 more. I labeled that one 1. I've got a 2 and a 3, but it comes after this next thought. And my next thought is this. The logic of a randomized comparative experiment. So I'm interested in this part right there. In other words, what kind of conclusions can I draw after the fact? Well, there's a couple thoughts. My first thought is, it's designed to give good evidence that the difference in treatments, when I say difference, the difference in the response variable due to the treatments actually causes the difference we see in the response variable. Now you see that whole big thing I got written there? What they're telling me is this. This whole randomized comparative experiment is supposed to give me good evidence of cause and effect. I make changes in your explanatory variable that actually causes the changes in your response. Oh yes, I got it. You know, the explanatory variables, now they're called factors. The factors and their levels make up the treatments. That's the bottom line here. The randomized comparative experiment is set up and designed to give you good evidence of causation, cause and effect, if there is any. The way this works is like this. I've got three thoughts here. One, we do the random assignment. You know, the randomization. And what that does for us is it produces similar groups, treatment groups. The lurking variables are working on all your groups in this randomized assignment. Two, the comparative part, right, the comparative design where we know we're going to compare treatments, the only difference between these groups that we randomly make are the treatments. Look, I didn't write anything down that you haven't already talked about tonight here. It's number 3 that's of interest. Alright? That's the randomized comparative part. Number 3 is what we're interested in. Right? Okay, so you've done all the right stuff. You randomly made the groups, so that produces similar groups. You're going to use the comparative part, so the only difference between your actual groups are the treatments that you're interested in. And now it's number 3. This is the new part. Okay, so what kind of thing can I say after the experiment's over? Now, the differences in the response variable. Okay, are due to if there was just one, I'd be a happy camper. But the problem is there are 2. Now, everybody put everything down for a second. I want to go back here to this little outline I drew. All right? So let's say we actually did this experiment, right? You got the 50 students. We gave 25 of them the classroom version and 25 the online version. At the end of the term, right, we give them the GMAT test, and we start comparing the scores of this group with this group. Let's say we take the average of each one and compare, right? So let's say the classroom version gets an average of 72% on the test. And the online version gets a 71%. Is there anything else? In other words, how they took the class, did it make a difference? 72 compared to 71, shit. See, here's the thing. Anytime I do a randomized comparative experiment, I'm expecting to see small differences no matter if the treatments had any influence on anything. So that's the reason I said, okay, let's say the classroom version had a 72 average, the online version had a 71. The hell, that's what you were expecting at the class, how they took the class didn't matter, correct? What about 73, 71? 2 points on a 100-point scale? No. What about if the classroom version has an 80 average and the online version has a 60 average? Oh, now my man in the back, he's shaking his head going, shit, dude, there's something up. Now, you're off by 20%, right? There's something going on. So I think about it like this. If the treatments don't have anything going on, in other words, the treatments have no influence on the response variable, I expect the scores to be close together. I expect the response variable for the different groups to be close. And as I start doing this, what's up? The further they get apart from the classroom version and the online version, the further the average scores gets apart, there's something going on, correct? That's where I'm at here. So I guess I could put the word like 80-60, like 75-62. 72, 71, 73, 70. No, that's not, that's what I'm expecting if the way they took the class doesn't make a difference. I don't expect them to be 72, 72 if the treatments don't make any difference. I expect some small differences, even if the treatments don't. I'm looking for large differences, 80, 60, 75, 62, right? My problem is, you notice I've got a 1 or a 2 here. What we're wanting to happen is, that's what the hell we want to see. We want to see these large differences in our response variable, like an average score of 80 versus an average score of 60. We want it to be due to the actual treatments. In other words, how they took the course, right? That would tell me that we have evidence of cause and effect, causation. Okay? The problem is number 2 here. That's what the hell we're looking for large differences. We want it to be due to the treatments. That's the reason we did this to start with. The problem is, it could be due to the play of chance. Yeah, we use chance here, right? We randomly assign. And what I mean by the play of chance in assigning the subjects to the treatments. And here's what I have in my mind. And I'm going to do this. I want to star this because that's what we're looking for. If we have large differences, 80 to 60, 75, 62, something like that, we want it to be due to the treatments. The problem is there's always this play of chance in assigning the subjects to the treatments. And here's what I mean. Is it possible, when I went back here, all right, and I did the randomized comparative experiment like this, is it possible that I assigned the 30 best students to the classroom version and the 30 worst students to the online version? Is that possible? Yes, shit, it is. It is, right? It's possible. That the 30 best students on that random assignment by choosing an SRS, the 30 best ones went into the classroom version, and then the 30 worst ones went in the online version, then what would happen? Obviously, the classroom version scores would be higher because you had the best students. The online class would be lower because you had the 30 worst students. So that's a possibility, yes? So then the question is, how do I get around this? How do I fix it so that's no longer a problem, that's random assigning of the subjects? You know, the play of chance that the best went here and the worst went here. Well, be able to repeat the experiment. Replication. I want to be able to replicate the experiment. What does that mean? Well, that means I'm not going to just do this one semester. I'm going to do this 4 or 5 semesters in a row. right? I'm going to do this randomized comparative. Let's just say for the sake of things, I'm going to do it for 4 semesters in a row. And it turns out every semester when I do that, the classroom version scores around 80 and the online version scores around 65. Now what's it due to? Well, it can't be due to number 2. Hell, we saw it 4 times in a row, right? 4 semesters in a row, we saw the same results from my rank. Now, obviously, these are different students all the time. And there's no way in hell, for 4 semesters in a row, I'm going to assign the best 30 chance to the classroom version and the worst 30. No, right? We've ruled that part out. In other words, if I can replicate the experiment and get the same results over and over again, I've ruled number 2 out. And what's causing those large differences? It's got to be the treatments. Anybody ever wonder why, forget classroom and online, you ever wonder why it takes a drug so long to come to market? What the hell are they doing? They just standing there like twirling their ears or what? They're taking care of number 2. Right? You know, they got something that they think helps for high blood pressure or whatever, right? You know, this will lower your high blood pressure. How come they just don't do one experiment and walk away and say, well, shit, it worked in that one, we should market this to the people? It could be due to chance. Why do they do this over and over and over again? They want to see the same results over and over again. That's the reason it takes like years for some new drug to come to the market, because they're doing this replication here. They're repeating the experiment. All right? Does that make any sense to anybody? So, you know, we randomly assign the subjects, we compare treatments. That's my randomized comparative part. Number 3 is, if we see large differences, we want it to be due to the treatments. How do we know that? Well, we're going to be able to repeat the experiment. We're going to replicate it and see the same results for, like I said, maybe 4 semesters in a row. The classroom version was always a large difference from what the average score was on the online version. All right? Now, I got a little box here I want to point out to you on page 240. And there's a little box and it says, principles of experimental design. These are good principles to follow. All of our well-designed experiments follow these 3 principles, and the first one is control. And what we mean is control the effects of lurking variables, through comparison. Folks, that's the comparative part. In other words, that experimental design principle is telling you that you don't suffer from confounding. 2. The second one is randomization. Right, I'm going to write it again for you. Use chance to assign subjects. Now, I don't know how many different ways I can write the same thing for you tonight. 1 and 2 is a randomized comparative experiment, right? You randomly assign the subjects to the treatment, and 1 is you always use comparison, and that's to control the effects of the lurking variable. That's the thing that was the first terms I wrote up tonight, randomized comparative experiment. And then number 3 takes care of my problem I had on the previous page, and number 3 says replication. Right? Be able to repeat your results. And I'm going to write it like this. Use enough subjects I'm just going to leave it like that. I don't really get too carried away with what the rest of it says. Use enough subjects in each group to reduce chance variation in the results. In other words, be able to replicate what you're seeing. Be able to have enough subjects so that you can replicate your experiment over and over again so you see the same result every time. Those are your three principles of experimental design. Control through comparison, randomization, and replication. And you're going, why are you doing this? Because on your next test, there's going to be a question that asks you about these three principles of experimental design. And the question says, which of the following is not one of the principles of experimental design? Three of them are comparison, control through comparison, randomization, and then replication. All randomized comparative experiments do this. Now, a little bit of language here. All right? And my little bit of language goes like this. We hope to see differences so large that it is unlikely to happen by chance. Now, when I say unlikely to happen by chance, I already know that we're going to be able to repeat it. So now I'm looking like at a single experiment. So I'm looking at 80 versus 60 on the scores, or 75 versus 62, right? I don't want that. If I know I can repeat it, then I know those can't be due to any kind of chance, right? This can't be the chance variation that we see here. See, a score of 72 to 71 or 73 to 70, that's just chance, right? I mean, hell, there's nothing up. The treatments didn't do anything. I want to see large differences. Now, the reason I underline that, I can't tell you how large needs to be at this moment. But I can give you a term, and the term we want here is statistically significant. Very, very statistician sounding. And statistical significance shows up on page 240. So I'm going to quote the definition to you. It says, an observed effect so large, so we're looking at large differences between the response variable for our different treatment groups, like 80, 60, 75, 62, that would rarely occur by chance is called statistically significant. Look, that's exactly what this back here. You know, we hope to see differences so large. We hope to see differences that we can call statistically significant, right? That they're not going to happen by chance. Something has to be up. And what that means is, everybody's going to tell you, statisticians, when you read any kind of research, they're going to tell you, hey, you know, the results of my randomized comparative experiment are statistically significant. Oh, really? Well, what that means to me is the effect you're seeing is so large that it can't be happening by chance. So if it's not happening by chance, what the hell is it due to? Well, when somebody tells you they have statistically significant results of a randomized comparative experiment, damn, it's like I got all kinds of big-ass words. Statistical significance, randomized comparative experiment, right? It means we have good evidence, which is what we set out to do this, that the treatments caused the differences. And I'm going to add a little bit to this in the response variable. So when somebody tells you we have statistically significant results from a randomized comparative experiment, they're telling you, look, you got good evidence that the treatments actually caused the differences in there, right? The differences are large, and the treatments are causing them. Well, what's another way to say the same thing? We have good evidence cause and effect. We follow all the little rules. We do the 3 principles. We do comparison, we do randomization, where we can repeat it. And every time we see these large differences between for the response variable amongst our treatment groups, we have statistically significant results. Okay? That means we have good evidence that the treatment actually caused the differences you're seeing in response variable. The only other way I can say it is, hey, we've got good evidence of causation. We've got good evidence of cause and effect. You start changing the value of your explanatory variable, it actually caused the change in your response. Now, the only problem we have is, the language is all perfect, right? A statistician is going to give you the statistically significant results, right? The other 2 here, so you know what they're talking about when they say that. Oh, we got good evidence of treatment causing differences. Or, we got good evidence of causation. The problem we have at this moment is how large does large need to be? And I can't tell you that at the moment. I can't tell you that, well, I can tell you this. 80 to 60? Yeah. 75 to 62? Yeah. What about 79, 72? 77, 70? The closer they get together, you understand, I'm moving my hands like this again, right? I'm expecting if the treatments didn't do anything for the scores to be close together. And as I start doing this, at some point they'll be far enough apart, there'll be large enough differences to say that the results are statistically significant. I can't tell you if it's a difference of 5 percentage points or 10 percentage points. There's a reason I chose 80-60. None of you would blink when I tell you there's something up at 80-60, right? There's a reason I picked 75-62. None of you would blink at 13 percentage points. There's a reason why I picked 72-71 when nothing was up, and that was what I was expecting, because I knew 1 point difference, you'd think, well, shit, it didn't matter how I took the class. Is 4 point difference enough? 5 points difference enough? I don't know. Eventually, I will come back to this part I have circled in red, and I will give you a calculation. It won't be the chapter like 14 or 15, but eventually we will get a calculation that says, okay, when these are 10 percentage points apart or whatever it is, we're going to say they're statistically significant. Now, it's just we're looking for large differences, and the language is, you give me a large difference, statistically significant. Treatment's causing. You got evidence of cause and effect. Are we okay? This is not my last talk about that term. We'll have a calculation later. Now, I got some cautions here. Okay, so we've done everything right. Randomize, comparative, replicate, all of this. And my cautions go like this. Okay? And the way I'm going to put it is pay attention. To the detail. Okay? Now, has anybody ever heard of a placebo? I don't think I mentioned that word last Thursday. Anybody ever heard of placebo? So if you've heard of that, then you've heard a thought about placebo effect. You know, where subjects will respond to any treatment because they're getting a treatment, right? They'll feel better no matter what because, hey, I'm getting a treatment, right? I'm going to start labeling these little guys here. What about a placebo? That's nothing more than a dummy pill that looks like the pill that everybody's getting, but it has no value to it or whatever, right? It's just like a sugar pill or something, right? You introduce a placebo to control for the placebo effect, especially when you're dealing with humans. I can't believe dogs and cats really know whether they're getting the treatment or not. People, they know, right? And so, just because the people are getting the treatment, don't think they're getting better no matter what, so you give them a placebo. Okay? Now, 3. There's something called the double-blind technique. And what I'm thinking here is neither the subjects for the experiment. How's the book say? What terminology they use? Or the people who interact with them know which treatment each subject is receiving. Students always get a little cross-eyed at me at this point. Right, so let's think we got some kind of pill that's going to help people with whatever. Depression or anxiety or whatever your thing is, right? And so, if I don't have a placebo involved and I just give that pill, people may, you may be seeing the placebo effect, right? They respond, they're less depressed or less anxious because they receive some kind of treatment. So we introduce a placebo, right? And we give that to control the placebo effect. Well, so here's the problem. Obviously, we never ever want the person to know whether they got the real treatment or whether they got the placebo, right? That would be single blind. Double blind, obviously you don't want the person, the subject to know, but you don't want the person handing the pill to the person to know whether they're getting the real thing or not because they might tip them off. By a look or blink or wink or whatever. That's double blind. Now, you do understand there's somebody in the back room that never interacts with the subjects that actually knows whether that was the real thing or not, right? That's what we mean by double blind. The person getting the treatment never, ever knows what they're getting. And in this case, double blind means the person handing them out doesn't know whether you're getting the real thing or not. That's double blind. Single blind would be the subject doesn't know. All right? Now, I got a story about all this. You don't mind? Can I tell a story? So, I got a habit. Yep. And it's been maybe 5 or 6 years ago. My wife thought it was a bad habit. So, one night I went home. And you ever see those nicotine patches? You buy the nicotine patches and you stick them on you and it's supposed to help you with your craving for nicotine, right? Well, it turns out that box of packages that my wife bought home was like $80. Yeah? Oh, it's a high dollar, it's supposed to do all this. And so I start reading the back of the box. And it says, they did a randomized, comparative, double-blind, placebo-controlled experiment. Shit, all the words I just told you. They randomly assigned subjects to the treatments. They compared treatments, right? The actual package against some kind of placebo control. Yeah? So it's got all my magic words we talk about in this class. Yeah? Yeah. So that's all on the outside of the box. Yeah, the words I want to hear. Oh, they did a randomized, and you're going, really? Yeah. Next time you're in, the drugstore or whatever, or Walmart, pull something up like something for coughs. Like the little Cody's tablets and stuff. Read the back of that package. They're going to give you all the magic words. Randomized, comparative, double-blind, placebo-controlled. Yeah, right? Yeah, so then I opened up the package of those $80 patches. There's a pamphlet. There's a reason why what was on the pamphlet was not on the box. It turns out that 52% of the people that actually took the patch quit smoking. Good, right? Better than a coin flip. And that wasn't the part that upset me about the $80. It turns out 47% of the people that took the placebo quit smoking. You understand why that wasn't on the outside of the box? The moral of the story is this. If you smoke and you think you want to quit, I have some patches in my office for $40 that I'll let you have. Hell, whether they're the real thing or the placebo or not, right? It was what, 51% versus 47? Shit, I gotta think your head out, right? I gotta give you another story too. I talked about, you ever seen the little coldies, like a little cough drop thing that's supposed to reduce your cold? Yeah? Oh no, they're like zinc in them. They taste like crap, but they're supposed to reduce your cold by like 42%. And on the back of the package it says, randomized, comparative, double-blind, placebo-controlled, all my magic words. The question I always have for these people is, if you're going to reduce my cold symptoms by 42%, how did you know how bad my cold was going to be before I got it? All right. I'm just trying to get you to be a better consumer. Sorry. If you didn't like either one of my stories, I apologize. And they're actually both true. Because my wife also brought home the coldies, and she said, you look like you're starting to get a cold. You should take one. You should put one of these in your mouth. It'll reduce your cold symptoms by 42%. Well, let me see that back. Randomized, comparative, double-blind. Yeah. Somehow they knew my cold was going to be this bad, so I was going to be this much better. One other one. Right? I gave you all these. Placebo effect, placebo. I try to give you like halfway entertaining examples of this kind of stuff. And then there's a fourth one. Okay? Lack of realism. All right, when you're experimenting, it's one thing. But when it actually gets put out in the public, it's another. And here's my thought. And I always like to read this example because I'm hoping at some point the author is going to change this one. Because most of you guys aren't going to have any idea what I'm talking about, but I'm going to read it and explain it to you. It says, I'm interested in example 9.8 here. Those center brake lights. It says, do those high center brake lights required on all cars sold in the United States since 1986 really reduce rear end collision? How many of you folks was actually born after 1986? Yeah, freaking all of it. So at some point, there used to be cars on the road where that big-ass red light in the back window wasn't there. Right? That's what they mean by the center brake light. In 1986, they thought, well, if I put that in there, that'll catch your attention, and we won't run over the person in front of us when we are stopped. Seemed like a reasonable thought, right? So they did an experiment. It says randomized comparative experiments, our magic words, with the fleets of rental and business cars done before the lights required showed that the third brake light reduced rear end collisions by as much as 50%. No shit, I can remember. I actually started driving. I'm sorry, I'm old. I started driving before those were actually in the back of the window. And then as soon as they put them in there, it was like, shit, there's this big red light in my face. I should stop. It turns out, though, after they were put in all the vehicles, it dropped to 5%. Well, what's the problem? It's a lack of realism, right? Once everybody has it, then it's just like anything else. It's like the two red tail lights at the bottom of the car. You just ignore them. Right? Okay. What kind of things do they do today like this? Anybody seen the brake lights now? You know, like they're LED and they go across the back. Oh, get all kinds of cool stuff. Blinkers. You got them on the mirror. I got them on the side of the car. They do a little back across. What happens after everybody has that? No, we're still running over people. We're still turning in the wrong lane. Lack of realism. You can't really experiment about this because once everything has the center brake light or the blinkers on the mirror or whatever else, it just becomes commonplace. And so that's the reason you see these car manufacturers are always changing something, right? They're always changing how the lights look or where they're located, just to try to catch your eye. What they need to do is they need to put it like on your steering wheel. So when you're looking down at texting, it would tell you. Then you got a shot at mixing that guy in front of you. That was all in fun too. Okay. Now, I'm back to experimental design. I'm going to give you two more. The first one was completely randomized. All in a pile, randomly assign them to the treatments. 2, matched pairs. Design. It's still a randomized comparative experiment. It's how we set it up. Now, the problem with matched pairs. Only 2 treatments Completely randomized, I can have as many treatments as you want. My diagram just gets bigger with more treatment groups. But with matched pairs, we can only have 2 treatments to compare. So, matched pairs comes in one of 2 ways. I'm going to say it out loud to you because you'll remember. You take your subjects that you want to experiment on, and you match them as close as possible to whatever variables you think are important. Maybe you do it by gender, their age, their education level, and you match them. So I take all my subjects and I have these pairs, right? So I got this pair, that pair, and so on and so forth. You know, I might end up with 50 pairs when it's all said and done. Then what you do is you flip a coin to see which one in the pair gets treatment 1 and which one in the pair gets treatment 2. Then after they've had the treatments, what do? You compare the results, that response variable, on the pair. That pair will give you a result, that pair will give you a result, that one will give you a result. That's one way to do matched pairs. The other way is treat every subject as the pair. It's matched as close as possible to itself, right? It's the same person. Flip a coin. They get treatment 1 first, wait a week, and then they get treatment 2. And then you compare the results on the 2 treatments on that one individual that we're treating as a pair. That's matched pairs. I can't really draw you a nice picture of this. I mean, I always think if I was going to draw you a picture, you know, I'm going to match, right? So I'd have a whole bunch of these. I'd have subject 1 and subject 2. I can't really say groups. I can't really say anything was randomly assigned. We matched them, right? By, like I said, you might match them by their gender, their age. That's a couple that are common. And then this one we get treatment 1. This one we get treatment 2. You're only allowed to have 2 treatments. And then how's the comparative part come in? You compare the response variable on those 2 pairs, on those 2 subjects. The catch is, here, you do the randomly assigned. And what I mean is, flip a coin. Heads, subject 1 gets treatment 1. Tails, subject 1 gets treatment 2, and the other one gets the other. So is this a randomized comparative experiment? Is it limited more than a completely randomized? Yeah. You can only compare 2 treatments. Now, you would have a whole bunch of these, right? You'd have this pair, that pair, and so on. Or if you want, think about you have a single subject, and then they get each one of the treatments, and then you compare. All right? I got to look at this little example here. Sometimes a matched pair is actually better than completely randomized. For example, I'm going to make it up. All right? Let's go back to my driving. Right? So what we want to compare is we want to compare how fast you brake without a cell phone and with some hands-free cell phone in the car. Right? That's the 2 treatments I want to compare. You know, with no cell phone in the car, and then you're not holding it. You know, you got it, so it's talking to you. How fast do you brake when something shows up in front of you that you should stop? Now, what's the problem with a completely randomized design? In other words, I got 40 people that I want to experiment on. So I randomly assign 20 of them to drive without any cell phone, and I assign the other 20 to drive with a hands-free device, right? What's wrong with completely randomized? You ever heard the term you're comparing apples and oranges? You understand, these people's reaction time here are different than these people no matter what the hell's in the car with them, right? So I'm comparing apples and oranges. What would be a better way to do this? It would be matched pairs, treating every individual as a pair. 1 week, let them drive without the hands-free. See how fast they react. Come back 2 weeks later, let them drive with the hands-free and see how fast they react. Then I'm comparing apples and apples. Matched pairs would actually be better like that. Okay? My 3rd experimental design is just a really like a blowed up version of a matched pairs. It's a block design. before you ever do anything, you divide the subjects into similar groups called blocks. I got to ask this question. Where else do we do this? What sampling design do you divide the population up into similar groups before you start doing anything? That's your stratified random sample, right? Stratified random sample is a sampling design. Block design is an experimental design. It's how to do a randomized comparative experiment. Now, what we do is this. We use information about the subject's reaction to the treatments to form the blocks. In other words, you know something up front, and I got two of them in my mind. It turns out that men and women respond differently to advertising. Men and women like different types of advertising for the same product. It also turns out that men and women, they react different to certain treatments for cancer. That would be something good to know up front. So what we would like to do is this. I'm going to do this with ads, and I've got 3 ads for whatever you want to think about that you're trying to sell, right? And I know before I ever start this randomized comparative experiment that men and women react differently to advertising, right? So I want to know what would be the best to show the men and what would be the best to show the women, right? Okay, so my outline of this block design goes like this. Here are my subjects. There's nothing random to start with because I know men and women react differently to advertising. So I'm going to do a block design, and I'm going to say you're blocking. That might be a little fancy for us. Blocking variable is their sex or their gender. Because I know they respond differently to certain types of advertising, I'm going to use that to my advantage. So your first move, I'll put that right back. I just needed to move it down a little bit. My first move is form your blocks. That's the variable you want to go by. That's that categorical variable that we know it's going to make a difference, right? Because they respond differently to advertising. And then what we do is you just do the experiment on each block. In other words, if you don't mind, we're going to shorthand group 1, group 2, group 3. This is going to be your random assignment. In other words, you're going to look at the women and divide them up into 3 similar groups by choosing an SRS of whatever size, an SRS of whatever size, and what's left. And then this group is going to get add 1. That one's going to get add 2. That one's going to get add 3. Right? Then at the end, we're going to compare the response variable for just the women. So if I didn't know any better, that part looks right there, just like that completely randomized one I did before, except I'm only doing it on women. I'm going to do the exact same thing for the men. I'm going to do the random assignment, group 1, group 2, group 3, We're going to get add 1, add 2, add 3, and then here we're going to compare the response. That's the best outline I can do for a block design, right? What I'm doing is, if you think about it, I'm doing the experiment on the women, then I'm doing the randomized comparative experiment on the men. Is this a randomized comparative experiment? Maybe that should be my first question. You're randomly assigning the men to the treatment. You're randomly assigning the women to the 3 treatments. We're comparing within the women, and we're comparing within the men. Right? That's a randomized comparative experiment. The design is block design. How do I know that? See this part right here? We divided them up into these similar groups to start with. Now, what's so good about this? Well, you had information up front that men and women respond differently to advertising. Just for the sake of things, is it possible, doing things like this, that we find out that the women preferred ad 1, right? And the men preferred ad 2? What should you do with ad 3? Don't show that to anybody. Right? See, that's the advantage of the block design over, let's say, the completely randomized. You may not find this if all of a sudden you just put men and women together. You may not find anything. Here, I can actually tell you, well, this is the ad I should be showing to the women. You women can tell me, like, at what point during the day or the evening or what shows they should be showing that to you folks. If I know that ad 2 are preferred by the men, when should I be showing that? Football game, basketball game, give me some sporting event. Hell, that should be when you show that, right? See, what's good is we can draw separate, or we can draw conclusions about each block. And actually, I can also draw an overall conclusion, and my overall conclusion is throw ad 3 away. Women didn't prefer, men didn't prefer, throw this shit away. Right? So I can draw conclusions about each block, some overall thought about get rid of that one, right? Look, this is always better than anything else we can do because we had some information up front. This part right here, we use information about the subject's reaction to the treatments to form the block. We know something up front, we can do a better job. We can draw a conclusion about women, we can draw a conclusion about men. Now, just so that you have all 3 of these in one spot, experimental designs. One, completely randomized. 2, matched pairs. 3, block design. Now, I'm very hesitant to write on there what sampling designs match up with these. See, when I think of completely randomized design for an experiment, I think about a simple random sample for sampling. When I think about a block design for an experimental design, I think about stratified random sample for sampling, right? But here's the deal. Back in the previous chapter 8, we had sampling design. Simple random sample, stratified, systematic, multi-stage. Those are how you choose a sample. Here, I've got experimental design, completely randomized, matched pairs, block design. This is how you set up a randomized comparative experiment. This one here never goes over here. These over here never go over here. You understand? When somebody says, what kind of experiment are you doing? It's a randomized comparative, the good ones. When somebody asks you, what kind of experimental design are you using? You have only got 3 options. Completely randomized, matched pairs, or block design. Okay? If somebody asks you, what kind of sampling design, what kind of good sampling design are you using? Simple random sample, stratified, systematic, multi-stage. And sure shit, on the next test, I'll give you something, and it will be like a block design, and for some reason, I will put on there one of the answers as a stratified random sample, and somebody will pick that. Stratified random sample is not an experimental design, it's a sampling design. Alright, so can we move on now? See, the last two chapters, we didn't calculate anything, did we? You know, at least I got to draw some pictures. You know, I got to draw you an outline of a block design or an outline of a completely randomized. There wasn't any calculations. There's nothing here. This is all about the language, and can you pick out the little pieces that are going on here? All right? I prefer the next chapter much more because the next part we're going to talk about is, look, you've got to understand where we're at in the text. Right? Remember, the first 3 chapters went together, the next 3 chapters went together, and then these 2 here about samples and randomized comparative experiments about how we produce data, correct? You remember when I started with the sampling, and I drew you that picture about the population, then the sample, then I want to infer back? We need probability. And so we come over here to chapter, what's the number here? Chapter 12. And it's introducing probabilities. Page 277. Now here's the thing. I need this to continue. Because we're going to do, I think it's probably 2 chapters here of probability. I need that so that I can do the statistical inference I talked about in the sampling part. Being able to infer back about the population from your sample. All right? And should I need to with being able to try to infer back from some kind of randomized comparative experiment to the population, right? That data. I need this idea of probability. I need the language of probability. Now, the typical kind of question here about probability is example 12.1. This is a typical kind of statistician's question. And it says this. What proportion of all U.S. adults say someone in their household owns a gun? Now, you understand, we're looking at all adults in the United States. We're looking at millions and millions and millions, right? In other words, that's your population here, right? Your population is all U.S. adults. We're not going to ask every U.S. adult that question. We are going to choose a sample, or somebody's going to choose a sample for me. And it says, we don't know the answer to that, but we do have results from the Associated Press poll, AP GFK poll. The poll was a random sample. Oh, good word. I'm going to circle the good word. Random to me and you means they use chance, right? Nobody needs to tell me it's a simple random sample, stratified, systematic, and multi-stage. I'm looking for random because I know they use chance here. And how large a sample did they take? Remember, we use N for the sample size. I got to get you used to that one too. Lowercase n is always the sample size for me and you. So they chose a random sample of 1,009 adults. In other words, they had all the population of all U.S. adults, and they chose a random sample and came down here and had 1,009 adults, right? So from that population, they chose this. Well, with 1,009, they could ask them that question, right? Does someone in your household own a gun? And it turns out 353 of the people in the sample said that someone in their household owned a gun. So 353 said, yes, own a gun. Or someone in the household owns a gun. We okay? 353 said yes, that someone in the household owns a gun. Well, I need the proportion in the sample that own a gun. So I'm going to write sample proportion. I want you to know I'm getting ready to calculate something from your sample. So the proportion in your sample that said, yes, someone in the household owns a gun is 353 that own a gun out of the total sample size of 1,009. You pull the calculator out. I'm trusting the book. The 353 divided by 1,009 gives me a proportion of 0.35. Now you understand that 0.35 is about your sample. It was calculated from your sample, right? Does anybody want to talk about 0.35? And the answer is no. That's not the way we talk about it. How we talk about this? Exactly. I want you to be able to know where the proportion came from, because later when we do our work, it will be done in terms of the proportion. But people always want to hear, hey, 35% of my sample said, yeah, someone in my household owns a gun. If I put it in red, will this help? This right here is about the sample. You understand at the top, I really want to know about the population of all U.S. adults. All I really know about is the 1,009 random adults that was chosen and answered the question. You follow, right? So I'm up here, all U.S. adults. I chose a sample 1,009. I asked them the question, does anybody in your household own a gun? 353 said yes. That's 35% or proportion of 0.35, and that's about the sample. Yes? Well, so what the hell does that do for me? Well, I don't want to know about the 1,009. I want to know about all of them. Okay? I'm going to read the rest of it. If the sample was a simple random sample, it doesn't say that, it only says a random sample, then as discussed in Chapter 8, we talked about statistical inference, all adults had the same chance to be among the chosen 1,009. Remember? That's what a simple random sample does. It gives every sample of size 1,009 the same chance of being selected. That's the definition. It would be reasonable to use 35% as an estimate of the unknown proportion in the population. Use 35% to estimate the percentage or the percent of all U.S. adults. That would, I'm going to shortcut this, that would say yes to that question, right? That someone in the household owns a gun. You understand, right? So I'm just going to say yes. You see this little guy here? That's this idea of inference, right? We want to use what we calculated from our sample to infer back about our population, yes? Yeah, I'm going to say that again. I want to use what was calculated from my sample to infer back about my population. I want to take what I learned from the sample to say something about what I want to know in the population. It says, it is a fact that 35% of the sample said that someone in the household owned a gun. How do I know that? Where'd it come from? 353 out of 1,009. That is about the sample. That's the reason I put that in red for you. It also says, we know because the poll asked them. We don't know what percent of all adults would say that someone in their household owned a gun. No, we didn't ask them all. We know about the sample 1,009. We estimate that about 35% did at the time of the poll. This is a basic rule of statistics. Use results from a sample to estimate what you want to know about the population. I got all the U.S. adults. I want to know what percentage would say, what proportion would say that someone in their household owned a gun. Couldn't deal with them. 1,009, 353, 35%. I want to infer back. Might making any sense? That's a typical move of statistics. Use what you learn from the sample to say something about the population that you have no chance of dealing with everybody with. All right? Now, here's the thing. And I want to see how you do with this part. There's nothing here. You know, hell, I just read the problem and pulled this shit out. 100,009, 353, 35%. You could have done that. You didn't need me for that. Here's my question, though. If I take a different sample, of size n equals 1009. In other words, we played the game again. We took another random sample, 1009 adults. Are you expecting me to get exactly 353 to say yes this time? No. In other words, we would get a different and what I mean by a different result, you would get a different percentage in your sample that said someone in their house owned a gun. The first time we did it, we got 35%. Hell, the next time we get it, we might get 42%. We do it a third time, we might get 25%, right? Every time you would take a different sample of 1,009 adults, you're going to get a different result. Does that make sense? Have to, because you're getting different adults in your sample, they're going to answer the question different than the previous sample, right? You'll never get 35% when you're taking these random samples. You'll always get a different number. Okay? Now, with that said, random samples eliminate bias from choosing the sample. That was the point of using chance. We like that, right? That's the reason we decided to use chance, because we eliminate any kind of bias. The problem is, and what most people don't understand about all this stuff is they can still be oh, he wrote that word down? Yep, he did. They can still be wrong because of the variability that results when we use chance. In other words, the first time we did it, we got 35%. Is that right or wrong? Shit, I don't know. The next time I did it, I got 42%. Is that right or wrong? I don't know. The third time I did it, I got 22%. Is that right or wrong? I don't know. Right? So anytime you do this, you never know what you're right or wrong. Yeah, I know I did a random sample, so I eliminate bias and choose a new sample, but still, no, my results can be not even close. And when I say the variability that results when we use chance, you know, as I go from one sample to the next, whatever you're measuring is going to change, right? That's the variability. Yep. Okay. So what saves us from this? We need probability. I don't usually put exclamation points on things for you, but without probability, I might as well just go home and we call this semester spring break. Right? If we didn't have probability, we can't continue. Now, here's the thought I have. What this chapter is about, this chapter 12, it's about the language of probability. Yeah, am I going to talk a little bit about flipping coins, rolling dice, the roulette table? See, because here's my problem. And the statisticians in my department hate when I tell the students this. You start talking to me about probability, and on this hand over here is, look, the only reason I ever wanted to know any kind of probability is because I wanted to gamble, right? So probability gambling. Now, that's not all that's not all it is, but that's what I always have in my head. Probability, gambling, all the same guy. No, it's got its own uses here. And some of the things I'm going to show you is, like flipping coins, deck of cards, things like that, right? Stuff that people are kind of familiar with. Now, here's my thought, all right? The idea of probability. I'm going to make it as simple as possible. I always try to. Chance behavior. That's what I think about. Okay, so when you talk about to me about probability, I'm thinking about something that's exhibiting this chance behavior. And what I mean by that is unpredictable, in the short run, but as a regular predictable pattern in the long run. And what I mean is this. The simplest thing I can give you is toss a coin. I got a quarter. One side's head, the other side's tail. When I flip this coin, it is exhibiting chance behavior. And the way I mean that is, before I flip this coin, can anybody tell me whether it's going to show up to be heads or tails? And the answer is, hell no. Because if anybody can, right? In other words, before I flip this coin, if you can tell me heads or tails, and every time you are correct, me and you're going to take a trip west. Because I figure if you can do it with a coin, shit, what's the difference? You can probably do it with cards too, right? We'll take a trip to out west, all right? This is what I mean by unpredictable in the short term, right? Anytime I flip it, you can't tell me whether heads or tails shows up, can you? Nah, ain't nobody can. Because if you could, you wouldn't be sitting here listening to me. You'd already been out west. Okay? But let's say I flip it, and every time I flip it, I write down whether heads or tails shows up. Right? And I do it 500 times. How many times do you expect the head to show up? Oh, you guys all know it's about half, right? So if I do it 500 times, you're expecting somewhere close to 250 as long as my coin is fair. Folks, that's just what I got written down here on the piece of paper. It's unpredictable in the short term. Every time I flip it, you can't tell me head or tail. But if I do it long enough, does it settle down to a regular predictable pattern? Yeah. Half the times head shows up, half the times tail shows up. Tossing a coin is showing you chance behavior. As simple as I can make it, that's the simplest one I can do. Right? Tossing a coin, head to tail. That's chance behavior. That's a good place to start. Now, you see on page 279, there's this little graph up here, this figure 12.1. I would like when, if you don't have your book, when you get to where you can see your book, would you please look at this on page 279, figure 12.1. So what they've done is they've taken this idea of tossing a coin, and they do it over and over and over again. But every time they toss it, they calculate the proportion of heads. Right? And they did it twice. There's one there in black and there's one in red. And what this graph looks like is this. So there's this dashed line here at proportion being 0.5. Right? And what it does is, as they toss it, what you'll notice is one of these it comes up here and does this, and then we do that. And then the other one does, well, it starts up and goes here and does this, and then does that. This right here is around 50, and that is the number of tosses. So what they did was they tossed it, heads or tails. Then they figured out the proportion of heads out of one toss. They tossed again, proportion of heads out of 2 tosses, 3 tosses. Every time they recalculated proportion of heads. You notice, after about 50 tosses, what's the proportion of heads settled down to be? It settled down to be around 50%. You already knew that was going to happen if your coin is fair. That's what's going on here. So now I've got a couple thoughts. Example 12.3, we got some guys that had some time on their hands. It says the French naturalist Count Buffon, 1707 to 1788. I mean, he was in the 1700s, so what else did he have to do? Tossed a coin 4,040 times, results 2,048 heads, a proportion of 0.5069. Are you shocked? Close to 50%, right? Around 1900, the English statistician Carl Pearson heroically tossed a coin 24,000 times, results 12,012 heads, proportion of 0.5005. Are you shocked? When did he do that? 1900. He didn't have much else to do. The only guy out of the three that had a reason was while imprisoned by the Germans during World War II, the South African mathematician John Carriage tossed a coin 10,000 times, results 5,067 heads, a proportion of 0.5067. Let's go home. I got time. It's time to go. When I come back on Thursday, I'm going to give you the definition of randomness, and even more important than that, the definition of what does probability mean? How do we think about probability in this class? Be careful going to the house. We will see you on Thursday.